You have learned that in case of functions with one independent variable, the derivative gives the rate of change in the dependent variable when independent variable changes by a small amount. When more variables are involved, they may often vary independently of each other. It is often useful to look at the change in the dependent variable when only one independent variable changes and the others are held constant. Partial derivative measures precisely this change and is denoted by the symbol delta. In this module, you shall be introduced to the concept and interpretation of partial derivative of the first order, partial derivatives of the higher order, various rules governing partial derivatives, in particular the chain rule and the notion of Hessian matrix for multivariate functions. After studying this module, you shall be able to know the concept of partial derivatives and their interpretation. Learn finding the partials of higher order. Identify the changes in dependent variable that have been caused by changes in different independent variables. Evaluate the partial derivatives for multivariate functions. Understand to use the chain rule in finding partial derivatives involving composite functions. Know the concept of Hessian matrix and its relevance. Learn the notion of differential of a function and apply it for finding approximate changes in functions. Now we shall discuss about partial derivatives. Consider the function z is equal to f of x comma y. This function will have two partial derivatives or simply first order partials, one with respect to x and other with respect to y. Partial derivatives with respect to any one of the independent variables, say x, indicates the variation in the function as only x is varied and y is held at a constant value. Example, z is equal to fxy is equal to x cube plus 3y square plus 2xy. The partial of the function with respect to x is given by 3x square plus 2y. The partial of the function with respect to y is given by 6y plus 2x. The following notations are commonly used. Delta z by delta x is equal to delta f of x comma y upon delta x equal to delta f upon delta x is equal to f of x for x comma y, f of 1 for x comma y, this is equal to zx, this is equal to fx, this is equal to dfx to represent the partial derivative of the function with respect to x. And delta z by delta y is equal to delta f of x comma y upon delta y is equal to delta f upon delta y is equal to f of y of x comma y is equal to f of 2 of x comma y is equal to z of y is equal to f of y is equal to dy of f represent the partial derivative of the function with respect to y. A formal definition of partial derivative can be written just as in case of an ordinary derivative as f of x comma y is equal to limit of f of x plus h comma y minus f of x comma y upon h as h tends to 0 and f of y of x comma y is equal to limit of f of x comma y plus h minus f of x comma y upon h as h tends to 0. The definitions above show that in each case one variable changes while the other remains constant. First order partial derivatives can thus be differentiated again with respect to both variables. Delta z by delta x, when partially differentiated with respect to x and y, gives delta square z by delta x square and delta square z by delta x delta y respectively. Similarly, when partially differentiated with respect to x and y gives delta square z by delta x delta y respectively, delta square z and by delta y square respectively. Equivalent notations frequently used are given as delta delta x of delta z by delta x is equal to delta delta x of delta f by delta x is equal to delta square z by delta x square is further equal to delta square f upon delta x square, which is equal to delta square f of x comma y upon delta x square is equal to zxx. It is also equal to z11 equal to f of xx equal to f of 1, 1. Similarly, delta upon delta y of delta z by delta x is equal to delta upon delta y of delta f by delta x is equal to delta square z upon delta y delta x is equal to delta square f upon delta y delta x is equal to delta square f x comma y upon delta y delta x is equal to zxy is equal to z of 1 2 is equal to f of xy is equal to f of 1 2. Delta delta x of delta z upon delta x is equal to delta delta x of delta f upon delta x is equal to delta square z upon delta x delta y is equal to delta square f upon delta x delta y is equal to delta square f of x comma y upon delta x delta y is equal to z of yx is equal to z of 2 1 is equal to f of yx is equal to f of 2 1, and delta by delta y of delta z by delta x is equal to delta by delta y of delta f by delta x, which is equal to delta square z upon delta y square is equal to delta square f upon delta y square is equal to delta square f of x comma y upon delta y square is equal to zyy is equal to z22 is equal to f of yy is equal to f of 2 2. According to the Young's theorem, cross partial derivatives of the same order are equal provided they are continuous and involve same number of differentiations with respect to each variable. Here is an example of Young's theorem, that is delta 5z upon delta y cube delta x square is equal to delta 5z upon delta x square is equal to delta 5z upon delta y delta x square delta y square is further equal to delta 5z upon delta x delta y cube delta x and so on. In each of these partials, a given function is differentiated 5 times, thrice with respect to y and twice with respect to x. The order of the differentiation is immaterial. Recall that an ordinary derivative dy by dx at a given point on the function y is equal to fx represents the slope of the curve at that point or the slope of the tangent line at that point. A positive derivative indicates a positive slope of the curve, while a negative one indicates that the slope is negative for the curve. Sign of second derivative tells whether the slope of the curve is increasing or decreasing at the point in question. Given the function z is equal to fx comma y, the signs of various partial derivatives can be similarly interpreted. The adjoining figure 1 illustrates the partial with respect to x, delta z by delta x measures the slope of the tangent line Lx to the vertical plane sections of the surface in the direction of x-axis. Similarly, delta z delta upon delta y measures the slope of the tangent line to the vertical plane sections in the direction of y-axis. If at x is equal to x naught and y is equal to y naught kept constant, delta z by delta x is greater than 0, this implies that the value of the function increases and the surface rises in the direction parallel to x-axis as x increases, while y is kept constant. A negative sign of partial implies a fall in the value of the function and the associated surface in the same direction. If delta z by delta x is equal to 0, it implies that the surface is neither falling nor rising at x is equal to x naught. Figure 1 shows that the surface falls when x increases or decreases from x equal to x naught. This is indicative of delta z by delta x at x equal to x naught is 0. The interpretations for delta z upon delta y are similar but in the direction parallel to y-axis. If delta square z upon delta x square is greater than 0, then the function changes at an increasing rate as x increases from the given point, and the surface is convex from below in the direction of x-axis. If delta square z by delta x square is less than 0, then the function changes at a decreasing rate as x increases from the given point and the surface is concave from below in the direction of x-axis. This interpretation for delta square z by delta y square are similar but in the direction of y-axis. Now we will discuss partial derivatives with many variables. The concept of partial derivatives can be extended to case of any number of variables. Let z be a function of n variables, that is, z is equal to f of x1, x2 up to xn. Delta z by delta xi represents the partial derivative of the function with respect to the ith variable when all other variables are held at a constant value. Thus, there exist n partials of first order, one for each I equal to 1, 2 up to n. Each of these partials will be in turn give rise to n partial derivatives of second order. The total number of second order partial derivatives for a function of n variables will therefore be n into n, which is equal to n square. When function involves many variables, the second order partials will become unmanageable. To keep them handy for practical analysis, they are usually arranged in the form of a matrix called Hessian. Hessian is thus a matrix of second order partial derivatives and is written as H equal to f of 1, 1, f12 up to f1n, f21, f22 up to f of 2n, f of n1, f of n2, f of nn. Hessian will normally be a symmetric matrix as most functions commonly encountered satisfy the conditions of Young's theorem and their cross derivatives are therefore equal. Let us take an example. Let z be equal to 3x minus 14y square plus 3r plus 2x cube minus 2xr plus 6sr plus 13xy. We have to calculate first and second order partial derivatives and write the Hessian matrix. The first order derivatives are delta z by delta x is equal to 3 minus 2x plus 13y. Delta z by delta y is equal to minus 28y plus 13x. Delta z by delta r is equal to 3 minus 2x plus 6s. And delta z by delta s is equal to 6s square plus 6r. The Hessian matrix can be written as H is equal to 0, 13, minus 2, 0, 13, minus 28, 0, 0, minus 2, 0, 0, 6, 0, 0, 6, 12, s. It may be noted that the Hessian is symmetric. This verifies the Young's theorem for the given function. Next, we will discuss the chain rule. Given z is equal to f of xy and x is equal to f of t, y is equal to gt. Here both the independent variables x and y depend on a third variable t. Then z effectively becomes a function of t, that is z is equal to f of ft comma gt, which is equal to ht. The chain rule is a helpful tool for analyzing rates of change for composite functions and is capable of incorporating additional variables and different types of relations. According to the chain rule, the change in z when t changes is given by dz by dt is equal to delta z by delta x into dx by dt plus delta z by delta y into dy by dt. Let us take an example to understand the concept better. Consider the function z is equal to 2x cube plus 3y square. X is equal to 3t and y is equal to t minus 1. We need to find dz by dt. Using the formula for the chain rule, we get dz by dt is equal to delta z by delta x into dx by dt plus delta z by delta y into dy by dt, which is equal to 6x square into 3 plus 6y into 1, which is further equal to 18x square plus 6y. Substituting for x and y, this gives dz by dt is equal to 18 into 3t whole square plus 6 into t minus 1, which is equal to 162t square plus 6t minus 6. Now find dz by dt by substituting for x and y in the function itself and then finding the ordinary derivative. Thus, z is equal to 2 into 3t whole cube plus 3 into t minus 1 whole square, which comes out to be equal to 54t cube plus 3t square minus 6t plus 3. This gives dz by dt is equal to 162t square plus 6t minus 6. Note that this is the same as obtained using the chain rule. Differential or the total derivative gives the total change in the function when changes in the independent variables are accounted for. Consider first a differentiable function in two variables, that is z is equal to f of x comma y. Z can change due to changes in x called dx and changes in y called dy. Then differential of z denoted by dz or df is defined as dz is equal to delta z by delta x into dx plus delta z by delta y into dy. If y is kept constant, that is dy is equal to 0, this implies dz is equal to delta z by delta x into dx or dz by dx is equal to delta z by delta x. Similarly, if x is kept constant, dx is equal to 0 implies dz is equal to delta z by delta y into dy, or delta z by delta y is equal to dz by dy. A partial derivative can thus be regarded as a ratio of two differentials. It is possible to calculate second and higher order differentials directly by applying various rules of differentials. Second order differential can be calculated as differential of a first order differential. Consider again z is equal to f of x comma y. dz is equal to delta z by delta x into dx plus delta z by delta y into dy. Second order differential d square z, which is equal to d of dz. While finding differential of dz, it is to be remembered that the terms delta z by delta x and delta z by delta y are both functions of x and y. Thus, d square z equal to d of dz is equal to d of delta z by delta x into dx plus delta z by delta y into dy. On further differentiating, we get d2z equal to delta by delta x of delta z by delta x into dx plus delta z by delta y into dy whole multiplied by dx plus delta of delta y of delta z by delta x into dx plus delta z by delta y into dy whole multiplied by dy, which is further equal to delta square z upon delta x square into dx square plus delta square z upon delta x delta y into dy by dx plus delta square z upon delta y delta x into dx dy plus delta square z upon delta y square into dy square. Applying Young's theorem, d square z is equal to delta square z upon delta x square into dx square plus 2 into delta square z upon delta x delta y into dx dy plus delta square z upon delta y square into dy square. In simpler notations, d square z is equal to zxx into dx square plus 2zxy into dx dy plus z of yy into dy square. When x and y change by a small amount, say dx and dy respectively, the actual change in the value of the function is given by delta z is equal to f of x plus dx comma y plus dy minus f of x comma y. It can be shown with the help of mean value theorem that if dx and dy are very small, then the differential of z, that is dz, is equal to delta z. This implies f of x plus dx comma y plus dy is equal to dz plus f of x comma y. This formula can be used to find the change in the value of a function when x and y change by small amounts. Let us take an example. The volume of a right circular cone of height h and base radius r is 1 by 3 pi r square h. If r is estimated with an error a and h is estimated with an error b, then show that error in the estimate of volume is given by 1 by 3 pi r multiplied by 2ha plus rb. Given volume V is equal to 1 by 3 pi r square h. Say this is equal to f of r comma h. dV is equal to delta V upon delta r into dr plus delta V upon delta h into dh gives the approximate error in the estimate of volume. Delta v by delta r is equal to 2 by 3 pi rh. dr is equal to a. Delta v upon delta h is equal to 1 by 3 pi r square and dh is equal to b. This implies approximate error is equal to 2 by 3 pi r h a plus 1 by 3 pi r square b, which is equal to 1 by 3 pi r into 2ha plus rb. The concept of differential can be easily extended to the case of n variables. Consider z is equal to f of x1, x2 up to xn. This implies dz is equal to delta z upon delta x1 into dx1 plus delta z by delta x2 into dx2 plus so on plus delta z by delta xn into dxn. The formal rules obeyed by differentials for practically differentiating a given function are exactly similar to those obeyed by the derivatives. Let f and g be two differential functions of n variables, f of x1, x2 up to xn and g of x1, x2 up to xn, then sum difference rule d of af plus minus bg is equal to adf plus minus bdg for any two constants a and b. Product rule d of fg is equal to f of dg plus g of df. Quotient rule d of f upon g is equal to g df minus f dg upon g square, where g is not equal to 0. Chain rule dg of f of x comma y is equal to g dash f of x comma y into df. Invariance property of the differential. The differential remains the same when the independent variables are free variables or are themselves functions of other variables. That is, if z is equal to f of x comma y, x is equal to f of tw and y is equal to g of tw, this implies z is equal to f of tw comma g of tw, which is equal to h of tw. Then dz is equal to delta z by delta t into dt plus delta z by delta w into dw, which is equal to delta z by delta x into dx plus delta z by delta y into dy. The above can be easily established by finding the partials of z with respect to t and w and using chain rule, substituting them in the expression for dz. Let us summarize what we have learnt in this module. Partial derivative with respect to any of the independent variables, say x, indicates the variation in the function as only x is varied and y is held constant. Each of the first order partial derivatives will in general be functions of both the variables x and y. This can thus be differentiated again with respect to both variables to get the second order partials. Hessian is a matrix of second order partial derivatives. Young's theorem, which says delta 2z upon delta y delta x is equal to delta 2z upon delta y delta x in case of cross partial derivatives of second or higher order, the order of differentiation is immaterial. Delta z by delta x measures the slope of the tangent line to the vertical plane sections of the surface in direction of x axis. Delta z by delta y measures the slope of the tangent line to the vertical plane sections in the direction of y-axis. The second order partials tell about the curvature of the relevant plane sections of the surface. The concept of partial derivatives can be easily extended to case of any number of variables. The partial derivatives obey the standard rules of differentiation, that is, the sum rule, the difference rule, the product rule, and the quotient rule. The chain rule is modified to incorporate more variables. Given z is equal to f of xy, where x is a function of t, that is x is ft, and y is equal to gt, then it says dz by dt is equal to delta z by delta x multiplied by dx by dt plus delta z by delta y multiplied by dy by dt. This can further be modified to incorporate more variables and complexities. The differential of a function z is equal to fxy is defined as dz is equal to fx dx plus fy dy. It gives the total change in z when change in all independent variables is simultaneously considered and obeys the standard rules of finding derivatives. If dx and dy are very small, then dz is equal to delta z is equal to f of x plus dx, comma y plus dy minus f of x comma y, that is f of x plus dx comma y plus dy is approximately equal to dz plus f of x comma y.